Hi, I want to talk today about proving properties of vectors, not just the property, what the properties are, but how to, in a mathematically rigorous way, show that it's true or show that it's false. So, in particular, I want to start with the operation known as magnitude. So the definition for magnitude, let's get that down. A vector with n components. You take a vector in n-dimensional real Euclidean space. If you write it out in component form, right? So it's written with components 1, 2, 3 up to n. Maybe it stops at just 2 components, in which case we call them x and y. Maybe it stops at 3, in which case we usually call them x, y, z, or maybe it just goes on to n components. What does the magnitude look like? So here's the definition of magnitude. The magnitude, which is written with sometimes just absolute value bars. Sometimes you'll see it just like this. Sometimes it's written with double absolute value bars to indicate maybe it's a more generalized version of absolute value that applies to vectors and not just to single numerical quantities. I usually write the double absolute values. So, but you'll see single absolute values in other contexts, absolutely, or other sources, right? Other texts, other notes, other videos. So double absolute value bars signifies magnitude for us, and the definition of magnitude is it's the sum of squares of the coordinates. So this is the definition of magnitude. Where does this come from? Well, it generalizes what we mean by distance in 2 dimensions, right? If you have just the magnitude of a 2-dimensional vector, so let's do that. Let's do a calculation where we do the magnitude of just a 2-dimensional vector. Let's do 5, negative 12. Right? So what am I looking for? I'm looking for the length of this vector. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's my vector. And I want its length, right? That's the idea of magnitude, is what's the length of the vector. Well, how does this definition tell me to calculate it? It tells me to take 5 squared plus negative 12 squared, and then take the square root of that quantity. This is Pythagorean theorem, right? This is nothing more than Pythagorean theorem. Look at how this lines up. You have here, what's the 5 measuring? The 5 is measuring a leg in a right triangle, right? So there's the 5. And then the 12, or the negative 12, right, is also measuring a leg in a right triangle, right? So here's another leg, right? They're horizontal and vertical, so they're perpendicular to each other. So you have 2 legs in a right triangle. So then how would you get the distance, right, on that hypotenuse? Well, call it d, right? So what do you have? You have that d squared equals 5 squared plus 12 squared, right? If you take the square root of both sides, there's the magnitude formula. The negative doesn't matter. We're squaring it anyway, right? So that's where the distance, right? If you call that d for distance, right? You can see that it's just writing down the Pythagorean theorem and then taking the square root of both sides, right? And then here you could do the arithmetic, of course, right? 25, 144, right? You get 169, which is 13, right? That's a nice vector to take a magnitude of, right? You actually get an integer for the magnitude in this case, rather than some irrational number, which is what you usually get. So this is an example of calculating magnitude, right? This definition this definition is just the generalization of what happens in 2 dimensions when you do the Pythagorean theorem, right? You add the sum of the squares of the 2 components in 2 dimensions to implement Pythagorean theorem. If you have 3 components or 4 or n, you just keep on going. You just keep adding the squares and square root when you're done. So now you might say, okay, well, why do we generalize it this way? Why not generalize it some other way, right? Maybe in 3 dimensions, you should cube each of the components. Maybe in 4, or instead of square them. I don't know, maybe the 2 should become a 3, right? There are other ways you could generalize this definition, right? So why do we pick that generalization as opposed to some other? Because it has nice properties. It's an operation that has properties that tell us interesting things, that make it convenient to work with, that have nice structure, right? So that's what I want to look at. I want to look at proving a property of magnitude. Let's do that as an example. So for example, let's look at this. Prove that for all vectors v, right? And oops, sorry. Prove that for all vectors v, in n-dimensional real Euclidean space. Prove that the magnitude of one over v times v equals 1. Prove that, right? Let's prove this property. So what we're doing is we're proving that if you take a vector and you take 1 over, you divide it by its own magnitude, it produces a vector of magnitude 1. Right? So this would be a way to say it in words, right? If you want to say it a little more informally, right? You could say that is, if one takes a vector v and divides it by its own magnitude, it then has magnitude 1. Right? That's the claim here. And oh, you know what? It's false. What I said for all non-zero vectors. Right? You can't do this with the 0 vector because then the magnitude is 0, division by 0, blah 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 blah. Right? So yeah, you do need to throw out that case. It's a technicality, but it's important, right? For the sake of making it true. So let's look at how you would prove this. So what you would do is start with one side of the identity, right? And calculate until you reach the other side of the identity. Typically, it's easier to start with the more complicated side of the identity, but there are cases where you want to maybe start with the simpler side too. So let's do this. Let's do the proof. So the first thing I'm going to do is declare my variable. So I'm going to let v1, v2, v3 up to vn. Sorry. Let's declare the vector v and then we'll declare the components. So let v be an n-dimensional real vector, right? So that we can then write it with components, right? We can write v equal to v1, v2 up to vn for some v1, v2 up to vn in the set of real numbers, right? So this is our setup. We've now declared our variables, right? That's a very important part of doing a proof is establish the notation, say exactly what the notation means. Then we calculate the left hand, starting from the left-hand side of the identity, right? So we calculate, I'm going to do magnitude of 1 over magnitude of v, right? And this is what? Well, down here, I'm going to write the definition of magnitude. That's my first step. Is I'm going to write out the definition of magnitude. I'm also, while I'm at it, I'm also going to rewrite v using its components. So just plug in all the symbols inside. After I do this, what happens next? Well, I need to do the next operation. The first operation was that magnitude. The second operation is a scalar multiplication, right? This here is a scalar, right? And I'm going to multiply it into this vector, right? So how do we do that? Well, the definition of scalar multiplication is that it's a component-wise operation. You multiply each and every component by that scalar. Right? So take that scalar and multiply it into each and every component of the vector. Now, we can apply this next magnitude, right? So now I'm going to do this outer magnitude operation. What does magnitude tell me to do? Magnitude tells me to take each component right? Take each component, square it, right? Add them up and take the square root. Okay. When I do that here, the tops all become squared, and on the bottom, it cancels the square root in each and every case. Lots of \c dots here, right? Now I add the fractions, right? They all have a common denominator already. It's the same denominator in every case. And after you add those, you notice that the numerator is the same as the denominator. Well, dividing a quantity by itself produces 1. Square root of 1 is 1. Right? Thus, a vector divided by its own magnitude, or multiplied by 1 over its own magnitude, becomes a unit vector, right? A vector of magnitude 1. As long as the vector you started with wasn't the 0 vector in the first place. Right? And this is another way that we see it sometimes. Sometimes we'll write it like this. Even though it really is scalar multiplication, we'll write it by 1 over magnitude v. We'll write it as 1 over, or we'll write it as v over magnitude v. So you write it as division, just knowing in your head that it really means scalar multiplication of 1 over that quantity. But it's a shortcut we use. Another shortcut we sometimes use is if a vector has magnitude 1, we'll call it a unit vector, meaning a vector of magnitude 1, a unit vector, right? Unit length vector. So that's it. That's the end of our proof. Right? So at this point now we've established the truth of this statement. Right? How did we do it? First, set up your variables. Declare your variables. Very important. Give names to every object that you're going to use in the proof. Also, then calculate carefully. Just applying each operation usually in a vector identity like this. This is all you need as far as a proof technique. There are many fancier proof techniques out there. Proof by contradiction, proof by cases, proof by induction, right? Here, in this context, often you don't need those. There are some where we will, and we'll see those fancier ones further on down the road. But for many, you can do it as I did here. Start with one left or right-hand side of the identity. Just start applying those vector operations to the coordinates one at a time, working from the inside out, following order of operations, and eventually you prove that the quantities are equal, right? And we're done, right? So that's our first example of a vector proof. Right? Now, next, I would like to show you a disproof. So because it's a very, very, very different structure to disprove an identity than to prove an identity. So let's disprove the statement. That if you have a vector and you have a scalar, suppose you're wondering, can you factor that scalar can you factor that out of a magnitude, right? A lot of times we factor out constants, right? Think of derivatives, integrals, right? So you might wonder, vector magnitude. I wonder if I have a scalar, can I factor that out, right? This is worth asking. Well, it turns out to not be true. No, it's true in many cases, but it's not always true. Here's the thing. This statement says for all something, right? So notice that since it is a for all statement, right, I'm claiming that something happens all of the time. You only need to find one instance in which it fails. You don't need to do a big general proof like this with V1, V2, V3, right? You don't need that. You only have to find one instance in which it fails in order to disprove the statement, right? Right, so here's our disproof. Here, DPF, disproof. So since it is that's not a real thing, by the way. People write proof, no one ever writes DPF. It just struck me funny. Anyway, since it is a for all statement, we only need to provide a single concrete instance in which the statement does not hold. Right? You don't have to prove that it always doesn't work. You just have to prove that it sometimes doesn't work. Even just one time doesn't work, right? Think of if someone makes the claim, all cats are black, right? Well, you don't have to show them that all the cats in the world are not black. You don't even have to show them thousands or millions of non-black cats, right? You only have to show them a single calico, right? A single orange tiger, whatever it might be, right? Show them any single cat that isn't black, and you've proven them wrong, right? Same thing here, right? So you don't have to do anything general. You can be very, very, very specific. So what I will do here is I will just come up with a very specific example, and such an instance, by the way, is called a counterexample. Right, so a counterexample right? A counterexample is the name that we give for this is a really important term in mathematics, right? It's a counterexample is this concrete instance that disproves a statement of the form for all something, right? So that we call it a counterexample. It's an example that runs counter to the claim that's being made. Counterexample, hence counterexample. Right? And it's in this case, here's my counterexample. You can be very often we try to be as clean or as simple as you can with counterexamples. You can look for a messy, fancy one, but why, right? You try to pick something as clean as possible. So here we go. Here's my example. So choose, I'm going to choose my vector v to just be 1, 1, right? And I'm going to choose c to be -1. Then what do I have? The right-hand side of the identity, right? Here's the right-hand side, left-hand side, the left-hand side. Here we go. Left-hand side, let's look at the left-hand side of the identity, right? Is what? It's magnitude CV equals magnitude -1 times 1, 1, which equals magnitude of -1, -1, which equals the square root of -1 squared plus -1 squared, which equals √1 plus 1, which equals √2. On the other hand, the right-hand side of the identity is what? It's C magnitude V, which equals what? In this case, it equals -1 times the magnitude of 1, 1, which equals -1 times the square root of the sum of squares of the coordinates, which is -√2. Well, they're not equal to each other, right? They don't match, right? So there's our counterexample. Right? Now, this identity is almost true. Well, what happened here? They were just off by a negative sign, right? Magnitude is always non-negative. It can't be negative. Whereas if you pull out the C, if C was negative, then you get a negative number because the C is on the outside of the magnitude. So it's almost true, right? It is always true. So just a comment. It is always true that the magnitude of CV equals the absolute value of C times magnitude V. So you can't actually pull constants out of vector magnitudes. You just have to remember to take an absolute value when you do, right? So it was nearly true, right? but still, in the form that I stated it, that was not a true statement, right? And we came up with a counterexample. Right? So this is an example of how you would write a proof of a statement that is true, right? And also how you would write a disproof, namely provide a counterexample of a proposed vector identity that turns out to not be an identity, right? That's not true. I want to mention in both cases, it's not part of the proof to draw a diagram, but it often helps. It often helps you the proof just be a little more intuitive. So like the way I might imagine this, why would you suspect that something like this is true in the first place? Well, here's a vector v, right? And then magnitude of v is that length, right, is the length of the vector. So then you can imagine, okay, well, I'm going to take this vector v and I'm going to divide it by its own magnitude. So what happens? I'm scaling the vector down. That's what scalar multiplication does. That's why we call it scalar multiplication. We take a vector and we scale it, right? If you have v, 2v, 3v, half of v, right? Okay, well, if I take v and I divide it by its own length, I'm scaling it down by its own length. Where does it end up? Well, length 1. Say it used to be length 6. I divide it by 6. Now it has length 1, right? I scaled it down by a factor of 1/6. So you can imagine, scaling it down. Scaling it down here to, sort of shrinking it by its own length, and now it ends up on the unit circle, right? It ends up having just magnitude 1. So that's a way that a diagram can, it's not technically part of the proof, right? The proof is down here, right? This is the proof, but the picture, just gives you intuition, makes you suspect that it's true. It's why someone might try to prove something like this, right? And there's constantly a debate in mathematics, sort of in mathematics or meta mathematics or epistemology, or, well, let's just say philosophy, that it contains all those things. There's always debate in philosophy, in the philosophy of mathematics. Does it do we believe that theorems are true because we have proven them, or do we prove theorems because we believe that they're true? So, and it's a very interesting debate, actually. So, regardless, this one is, whichever side of that you land on, this one is certainly true, right? And there is that accompanying diagram. Also down here, even in a false one, sometimes a diagram can help you come up with your counterexample, right? Like here, you could think about the fact that if C is anything negative, then it's just pointing the wrong way, right? You're giving now a negative magnitude to a vector. So if you think about something like C equals -1 and draw a magnitude, right? Or just draw a diagram, it can be sort of helpful, right? You can think of our axes, you can think of some vector v, and then you think of C as -1. So it goes, it comes down here, right? C -1v is now down here, but the magnitude of that is still positive, right? Even though when the -1 is out front, you get a negative quantity. So that's all there is to that. All right, great. So that's an example of proving a vector identity and disproving a proposed wannabe vector identity that turns out not to be. Okay, the next thing I want to do is I want to introduce, I want to show one more definition and show another example of a proof, right? A different one that doesn't have to do with magnitude, just to see how it goes for another operation, right? So let's define the projection of a vector v onto W is here's a place where you really need a diagram. I mean, you can define it without a diagram, which is kind of brutal. Without. So here's what you do. You have vector W. You have vector V. And what the projection is it's that right there, right? It's the one nice way I think to think of it is it's the shadow that V casts onto W. It's if W were the ground, right? And your sun is at high noon, right? So the sun is up here. This is the ground, right? The sun is at high noon, shining down, shining down, shining down, right? So this is right. The sun is shining straight, all its rays straight down. See you imagine all the sun's rays right at high noon. All the sun's rays are coming in perpendicular to the ground, right? So that's what the projection is. It's the shadow. That's what we call it, projection, like a movie theater, projects the rays of light onto the wall. Same thing here. You have the rays of sun coming down, and it's the shadow that is projected by the one vector onto the other, where the other shows you the ground, right? And shows you what direction is that happening in. So this has a nice definition. So the definition of this is is something that's not super intuitive at first, but it turns out again, why do we pick sometimes these weird looking definitions? Well, because they have nice properties. It's because they do what we hope that they do. So here here's the formula for projection. So it's W, it's the vector W scaled by a particular quantity. It's scaled by the dot product V dot W divided by the dot product W dot W. So it's kind of an interesting formula. If you look, it has two dot products, right, between vectors, V dot W and W dot W. It also has a scalar product, right, a scalar multiplication, because notice here in this expression, I have vector dot vector will produce a scalar, a number, right, not a vector. Vector dot vector will again produce a number. So now I'm just dividing two numbers. So this quantity as a whole is just a number, right? This is just a scalar, not a vector. It's not a vector anymore, right? Even though we started with a bunch of vectors. So then this scalar will get multiplied by W, right? And that's going to give us the projection. So this is a very nice operation. Let me do just a short example of calculating projection before we prove a property of projections. So let's do this. So we do, let's see here, we're going to do, for example, calculate the projection of, let's do my favorite vector from before. Let's take 5, -12, right? Let's calculate that projection onto the vector 1, 1. Right, so I want the projection of V, which is 5, 12, onto the vector W, which is 1, 1. So let's get a diagram here. So let's see. So we have one, 2, 3, 4, 5, 1, 2, 3, 4, 7, 8, 9, 10, 11, 12. All right, there's my vector V. And then I have W is vector 1, 1. So W is really, really short compared to V. Right? There we go. Just a little more to scale. All right. Now, here's the idea. W determines what? It determines the direction of the ground, right? So before I calculate it, I'm just going to draw the picture. So there's the direction of the ground. And then we have the sun's rays. The sun's rays are all coming in perpendicular to the ground. Right? They're all shining like this at high noon. And in particular, some of these sun rays are going to cause a shadow to be cast from V onto W. All right, so these are the, there it is, perpendicular. Right? Right, so what happens then is I get this little vector right there, which I call projection. Right, that little orange vector is called the projection of V onto W. Right, so these, and now these sunbeams, they're not really there. I was just sort of using them as a reference, but that projection, that's really there, right? That's actually there. So let's now look at this. Let's actually look at this projection. Let's calculate the exact coordinates of it. So what do I have? I have the projection of V onto W, right? Which in this case is what? Well, you do V dot W divided by W dot W times W. Right? So what do I have? Up top, I have 5 times 1 minus 12 times 1. In the bottom, I have 1 times 1 plus 1 times 1. And over here, I have just 1, 1. So I get negative 7 over 2 times 1, 1. And now I do the scalar multiplication, and I get negative 7 halves, comma negative 7 halves. Right? We got it. There are the coordinates of our projection. I like how this worked out. Look at the diagram. You could see just from the diagram that the x and y coordinates both should have been negative. Right? We're clearly in the third quadrant there just by our picture. You can also see the numbers should have been a bigger than 1, 1. 1, 1 was really tiny vector compared to the size of that orange vector that we drew. So even just a crude diagram sometimes really helps. If we made a big error, you can catch it sometimes by saying, "Oh, that doesn't look like what the diagram is telling me," right? So it's very, very helpful. So there's an example of doing a projection. There's also then sometimes people will say, there's another term that people will sometimes use where they'll say the scalar projection. This is another definition, right? They'll say the scalar projection. If you hear that term, V onto W, that is the magnitude of the projection, of the vector projection, right? So if you want, you could, up here where we defined, I just wrote projection, but if you want, you could call this the vector projection, right? So there's the vector projection and the scalar projection. I defined it as a vector, right? But down here, you could say The scalar projection is the magnitude of the projection. Right, so if you want, you can write that the scalar, well, here, let me write this. So we can, in symbols, we can define it as this, right? That's a perfectly good way to define the scalar projection, right? It's the scalar, the number, whose magnitude is the, or who is defined to be the magnitude of the projection. In this example, for example, if we revisit this same example that we did before, right, you could say the scalar projection of v, which equals 5, -12, onto w, which equals 1, 1, is what? Well, it's the magnitude of the projection. We calculated that as -7 halves, -7 halves, right? So the scalar projection, what I'm doing is I'm calculating the length of the orange vector in this diagram. And I'm saying, how long is that little orange vector? So what is this? It's -7 halves squared plus -7 halves squared. Take the square root of that. And what does that become? Well, it's going to be 49 halves plus 49 halves, which is going to be square root of 49, right? Half of 49 plus half of 49 is a whole 49, which is 7. There we go. So in this case, the scalar projection of that first vector onto the second is just 7, right? This is, so that's, you could say up here, you could say this way to interpret that is the orange vector, right? Has length 7, right? That's how to interpret the scalar projection. I'm just saying how long is it versus the projection itself had direction and magnitude, right? It was an actual vector, x and y component. So there we go. That's an example of a scalar projection. So this now brings me to property. So here's a property that I want to prove. That 7, I claim we've kind of seen that 7 somewhere. And look where we have seen it. 7 there was a 7 in this calculation right there, right? Could it be coincidence? Sure, it could be, or maybe it's not, right? That 7 up top, where did that come from? That came from the numerator of the projection formula, right? What's the numerator of the projection formula? It's right here. It's this. It's v dot w, right? There's my numerator of my projection formula. So maybe that 7, maybe it's not a coincidence. What if we write down what we noticed there, thinking that's not a coincidence? So we'll try to prove it. What was that numerator? That 7, right? It was v dot w. But here I took a magnitude, so it's definitely not going to be negative, right? So that's why there was that -7 in the numerator. Well, slap an absolute value on. That'll handle the negative, right? So let's say this. This would be kind of cool. Prove that the scalar projection of v onto w is v dot w. Right? Nice interpretation of dot product. It tells you how long the projection of V onto W is the dot product, right? This would be pretty cool. The magnitude of the dot product, right? So let's try this here. Let's try to write a proof. So first, let's let V and W just be vectors of the same dimension n. And what I want to do is I want to then write out the scalar projection. By definition, right? We defined it as the magnitude of the projection of V onto W. Okay, what am I going to do? I'm going to plug in this. Right? I'm going to plug this in. The formula for a projection. Okay. Now, here's something cool. This is why I want to do this proof. This proof looks pretty different than the identity we proved before. The identity we proved before, the best way to do it was to get coordinates, V1, V2, V3, up to Vn. Here, I don't want to do that. If you can do that, but if you take this, in this case, if you go V1 through V2 up to Vn for V, and then go W1 through Wn for W, you can do it, but it's just a mess. Sometimes you can prove vector properties by using previously proven vector properties. That's what I want to do here. That's what I want to do here. So here's what I want to do. I want to take this scalar, this big fat scalar, and I want to factor it out of the vector magnitude. How do I know I can do that? It's a vector property. It's this, oops. It's this note right here. I didn't prove this example, but you could. It's, yeah, this example right here. It's our little parenthetical that followed the previous example, right? So it's just C here is that whole big ugly expression, V dot W over W dot W. That's C, that's the scalar C, right? So I'm following that vector property. And you could prove this using the V1 dot V2 out to Vn. You could write a proof of this, right? And in fact, that's an exercise in our overleaf document on this topic. So, so I'm applying this property, right? That's what I'm applying here. So, and I'll put a little side note. This isn't really part of the proof, but it could be. I'll put a little side note because because of this property, right? So I'm applying that where C equals that whole big fraction. All right, then what do I want to do next? What I'm going to do next is the absolute value of a fraction is just the absolute value of the numerator over the absolute value of the denominator. Right? So that's not really a vector property. Those are just numbers, right? And that's just the fact of absolute value. You can distribute it over a product or a quotient of numbers. Now, the next thing I want to do is I want to look at the denominator. The denominator, this is the magnitude of W squared. Why is this true? Well, this is another property of vectors. If you take a vector and you do the dot product with itself, if you do a vector dot itself, you get the square of the magnitude. This is also an exercise in our overleaf document on this topic. This is a famous property of vectors. And this is something you could prove with that previous technique, v1, v2, delta down to vn, plug it in, right? And these two quantities are equal, right? So here, then what happens? Well, you can cancel this a little bit. You can cancel a little bit here. Can't one of those, these are now just all numbers. This is just ordinary multiplication of, this is a number divided by a number times a number. So now, right, that you don't have to think about vector operations versus numerical operations. These are all just numbers. Okay. So we got to the end of the road here, right? All right. This is not what we claimed, right? What we ended up with is not quite what we claimed. And this happens all the time. You maybe make a conjecture, you go to prove it. That's not quite right, right? This happens all the time in mathematics. But that's one of the reasons we do proofs, is it helps you catch your errors, right? The rigor that's provided by, see up here, man, I was like totally flying by the seat of my pants. I was like, yeah, there's a 7 here. Yeah, there's a 7 up here, right? And I made a conjecture based on that. It's not bad that I made a wrong conjecture. It led me to the right one because it led me to try a proof, right? And it found the right, what I meant to prove, right? So then you go up and you adjust your statement, right? So this is part of why we do proofs in mathematics. It actually helps the, it helps the creation of mathematics, right? The act of trying to prove things. So let's adjust it, right? It now, instead of just saying the projection of v onto w is v dot w, which wasn't quite correct, it's v dot w divided by the magnitude of w, right? That's actually the scalar projection. So that's what I wanted to what we really should have been proving, right? And if you look back even further, you might say, well, what happened with this little observation, right? What the heck? There was that 7 up there, there was that 7 down here. It looked so good, right? Well then, see, this also is why you try to prove things. It catches errors. What did I do here? I squared the top, but not the bottom, right? I squared the numerator, but I never squared the denominator, right? Simple little algebra error. It led me to a wrong conjecture. But the proof, if you can write out a proof, right? This is the power and the value of proofs. You can write out a proof. It's not gonna let a little algebra error through, right? It'll catch it. It'll catch it for you, right? So this should have been root 49, square root of 49 over 2 squared plus 49 over 2 squared. That is the square root of 49 over 4, right? Which still becomes 7 on top, but then it becomes 2 on the bottom, right? And there we go. Now we're dividing by the magnitude there. So that's the oops. Yes, there's a 4 on the bottom. Oh, sorry. A 2 on the bottom, right? Because it's a fourth of 49 plus a fourth of 49. There's a 2 on the bottom. There we go. Right. So there's our answer is actually 7 over root 2. And that totally works because look at this. What's the magnitude of w? The magnitude of w is root 2, right? And what's the dot product of v and w? It's actually 7, right? There we go. Now our example matches the property, right? Matches the proof. So there we go. This is this is just a bit of showing, that nice feedback loop, right? You do an example, make a conjecture, try to prove the conjecture. Sometimes you go back and catch an error in your example. These things happen. So, all right, cool. So at the end of the day, what have we proven? We've proven that the scalar projection of v onto w is v dot w over w. Right? What's nice is in the case where W is, oh, and we can put our little box, right, our end of proof down here. What's nice about this, in the case where W happens to be a unit vector, then the dot product is just telling you the scalar projection, right? So dot product just means scalar projection if W happens to be a unit vector. So that's a nice observation, right? So note, if W is a unit vector, saying magnitude of W equals 1, then that denominator disappears, right? So it gives you a really nice interpretation of dot product, right? Why do we define dot product how in the way that we do? Well, because it tells you something nice. It tells you what the scalar projection is, right? It tells you the length of the shadow that a vector v casts onto a unit vector, right? That's what dot product tells you, right? If you dot with a unit vector, you get the length of the shadow onto that unit vector. So there we go. Now we have a geometric interpretation of dot product, which is really nice. So, all right, great. Thank you for watching. Just to recap quickly, at a high level, what do we have? We have 3 proofs in this document, right? We have one proof where we prove an identity, and they're all proofs of vector properties, right? We have one proof where we prove an identity is true by writing out coordinates for our vectors, plugging in the coordinates, and then just calculating until we see that everything is equal, right? That was the first proof. Then we have an example of a disproof, right? A disproof of an identity, which constitutes coming up with a very specific counterexample, right? You only need one counterexample. Be concrete. Don't use generic symbols like V1, V2, right? Be very concrete. Find a particular instance in which that property fails, and you have disproven it. You've said, hey, this is not an identity because look, there's my counterexample. It's the best way to go. Lastly, we proved something about scalar projections and dot products, right? A connection between the two. And here I didn't prove it by using coordinates. I did a coordinate-free proof, something maybe a little more elegant. I mean, sometimes a little trickier to get used to, but also certainly a little bit more elegant. I didn't go write V as V1 through Vn. I didn't write W as W1 through Wn. Instead, I just used previously proven properties of vectors to deduce a proof for a new property of vectors, right? Very elegant, very powerful. So throughout this semester, we'll do both of these, right? In your homework, we'll do both of these, or well, all three of these, right? We'll prove things using coordinates, prove identities using coordinates, prove identities without coordinates, just from properties, and we'll also sometimes disprove identities by finding counterexamples. So, all right, great. Thank you for following the lesson, and I will talk to you next time.